Next, I want to just quickly go through the source code that I've written so far. It's by no means complete yet. The line feed is still missing. It's not cleaned up. It's still only debugging code. There's no SPI interface to interface with Raspberry Pi. It's just UART for debugging for now. So yeah, but the main printer logic is implemented. So it's okay to at least give a quick overview. So at first we set up I/O pins, hardware modules like the UART or the timers. We configure here just the I/O pins for the stepper motors, for the solenoids and all that kind of stuff. After that, we call the function move carriage to far left, which will do what the title says. It will move the carriage to the far left where we have a limit until we hit a limit switch. That location is required to align the daisy wheel, which is the next step that we're doing, where it'll move the daisy wheel left for a full revolution, where we'll eventually hit a little pin and thus align it to a 0 position. Pretty simple code. And after that we reset the printer. This is not strictly necessary. I just noticed that when the hammer was engaged and then the motor and then power to the motor was cut, that then it sometimes got stuck in a weird state, and this should be able to reset that. It's not really needed. The original setup does not do it. It's only, this problem also only occurs if either the microcontroller software screws up or if power is removed during a printing option and you really need to hit a very specific point in time. Okay, after that, I currently just run the printer test function, which is a very simple state machine based design. Everything in this firmware is essentially state machine based, so that it can run multiple tasks in parallel. For example, we have the main function which controls the stepper motors, or stepper motor control is not written like like many of us would usually go about it, and that is like set stepper motor state to something and then delay ms something, next state delay ms, next state delay ms, and so on. No, it is written as something that needs, as a function that needs to be called over and over in a main loop, and that's what I'm doing here. So basically that is the user code. And then we're calling step perform movement, which will entirely handle the movement of the stepper motors. So as I'll show you in just a second, here in the user code, I'm just using target position, or sometimes I'm using the set target macro here to simply set where I want the stepper motor to be. And then I wait until the position is reached, and then I do other stuff. So for example, here I do wait until position is reached, then I arm the hammer, and then I move on with the code. So that's how this works. And if we take a look at the step perform movement function, it first of all checks whether whether the stepper is currently moving, and that means we might have to stop it, or if the current position is not the target position. So if we want to go somewhere else, if that is the case, then we have this block for thing here. That's essentially my implementation of a timer. This is it's essentially a one-shot block here. That we have CFG delay, which is set to a fixed to a constant value. All the CFG parameters are, and when calling block for, it's pretty simple. It checks if a timer is 0. If it is, then we set it to the value passed, and we return 1. So that means if we think about the if down further down, we enter the if, execute the code, and so on. But in the next iteration of the main loop, the timer channel will be set to time systicks, or will be set to time systicks, so it will not execute, and we will return 0. Thus, the code within the if block is not executed. And then we've got the timer vector, which simply decrements the timers if they are greater than 0, which means eventually this timer will reach 0 again, and then we will return 1 again, retrigger the timer, and that's how I get the timing done for all the stepper actions, because here in this block we actually now call the stepper next f function, which will, this is the function that is actually responsible for driving the stepper motors, so applying the bit patterns to the individual coils. Before that, we just do some simple stepper required direction call here, which determines in which direction the stepper motor, so forward or backward, has to move in order to reach the target position. If we just think about it in a very basic manner, it's if target position is greater than our current position, it is we need to move to the right, or we need to count upwards. If it's less than it, then we need to move to the left. There's some additional code in here which handles some wraparound logic. So that is used for the daisy wheel, because sometimes it might say we go from character 1 on the wheel to the second last one or something. Then of course it is stupid to go all the way forward, cycle through the entire wheel. It would be quicker to just turn back a couple steps, even if it goes over even if it goes over 0. So that's what this logic implements here. If we can go, if the shorter path is to go reverse, then we go reverse. Yeah, and that's what this does. It also detects if there's a quick reversal from we're currently going forward to we're now going backward without a 0 without stopping in between. Then we enforce a short delay, just because it might slip if we just reverse the direction as is. Yeah, then there's the step and next function. As I said, it will simply do a couple of things. It'll load the current port state, because this is a generic function for all the steppers. I can't implement a separate function for each of the steppers. So it's just way too much code. I'm already, I think, at 5K in terms of the code. Yeah, the next step is to calculate the next required step. Step means can be as a value from 0 to 3, representing the current state of the coils. So yeah, here you can see the state being applied. So for example, in case 0, we need to unset pin A and we need to set C. Here we need to unset B and set D, and that's just your average stepper motor driver pattern for high torque. There's also a couple things. If we stopped and we're now resuming, we need to first restore the state, the last state we had, in order to get a clean transition to the next step. And then down here's just some more logic, because we need to, when reversing the rotation, for some reason I need to do one more step than I would have if I had been moving in the same direction before. I'm not entirely sure why I need to, but that's what that code is for. And yeah, then of course we just need to write it to the corresponding port. Yeah, I think that's about the code. Oh, yeah, one more thing in the application. Of course, it needs to somehow know how the where on the daisy wheel each character is. So I have a translation table from ASCII to the daisy wheel, which is here just stored in the PGM space. Yes, that's pretty simple, and then just some URL to help us, which are just for debugging. They will be removed. As I said, I think it is a problem that I'm using printf at the moment, because I've seen some weird stuff where changing a completely unrelated line of code made the design break or work all of a sudden, and usually I think it was printf calls in some way. So I'm going to remove those. Here's how the configuration looks like for each stepper. This one's, for example, for the carriage. The carriage is connected to port C. It uses the TIM carriage timer ID. It has these pin assignments, so port C3, port C1, and so on. That's the delay that is to be used between or the time for each step. So the lower this value is, the faster the stepper runs, but we're also running the risk of skipping steps. So need to find a nice value that works, but is still fast. Here's the wraparound configuration. So here we can see the daisy wheel wraps around after 96 times 2 steps, because we have 96 characters and each character on the daisy wheel is 2 steps apart. Here's some more test functionality, which just allows me to do simple things like move the wheel by 1 character in each direction, do the alignment, and all of this separate from the startup procedure just for debugging. It's quite helpful here. Stuff like that, yeah. also uses the step perform movement function, so it tests those as well. Yeah, that's pretty much about it for now. Of course, this is just like in the initial version of the code, there might still be bugs in there. There are some things I don't even understand myself, how I implemented them, but they seem to work, so okay. Yeah, I think that's it for this video. I decided to split the code documentation off into a separate video because these are usually quite rambly and probably fairly boring, so I'm gonna give this a separate video and pull out the other one.